what we're going to be looking at here is what's called a dynamic equilibrium. So at the moment in this syringe, we've got two gases. We've got NO2, we've got N2O4. So they become each other at the same rate. So 2 NO2 turning into N2O4 has the same rate of reaction as 1 N2O4 turning into 2 NO2 molecules. So we don't actually see anything happen, it's just one colour. Because this is a gas equilibrium, there are two things that I can do to change it. One is I can change the pressure. If I was to draw this reaction out and have the NO2 on the left-hand side, there'd be two gas molecules on the left-hand side and there'd be one on the right. So if you do your balancing of your atoms, there's 2 NO2 going to 1 N2O4. Alright, so on the left-hand side of our equation, there are two molecules, as it were, and on the right-hand side there's only one. Alright, so it means that if I increase the pressure, the system will shift in a way to try to get the pressure back down. This is what's called Le Chatelier's principle. So if I increase the pressure, it will try to make this, it'll shift the equilibrium in the way of fewer gas particles. So there's 2 NO2 making 1 N2O4. So it'll favour the forward reaction if I increase the pressure. Now, this is a bit hard to see because I'm not going to be able to increase the pressure a lot. And the first thing that's going to happen is the particles will get closer together. So initially it's going to go darker brown regardless if I increase the pressure. What we're trying to look for is what happens after I've increased the pressure to see whether it changes colour again. And sometimes this is really hard to see if at all. So I'll try and get it to work. So I'm going to increase the pressure. We can see it go darker because the particles are together. And then I'm not sure if it'll be easy to see on the video, but I could definitely see that it started going a little bit paler. So that tells me that if it went paler after I changed the equilibrium position, so the pressure, then the N2O4 must be colourless because more N2O4 is being made. And the NO2 is going to be our brown gas in this example. The other thing I could do, without actually opening the syringe because it's a toxic gas, is I could decrease the pressure, and of course that'll spread the particles out, so it'll initially go paler, and then see if it then darkens up a little bit. So let's see if that's what happens. So again it goes a bit paler. I think it was a bit hard to see, wasn't it? It did actually technically go a little darker, but not a lot. So that's not a very good one for us to see with this particular equilibrium. But it is an important thing for you to know that pressure, if your system has gases in it, then a change in pressure will change the position of that equilibrium. It'll either shift towards the reagents, NO2 in this case, or towards the products, N2O4 in this case. Okay. Just like any reaction, there is an energy change when these two molecules turn into each other. So when this reaction occurs in the forward reaction and the reverse. Now this one's a little bit more obvious to see. So what I've got here is some hot water, recently boiled actually, and I've got some iced water. So I'm actually going to change the temperature of the system. Now the system is going to try to undo the change. So if I drop the temperature, it'll try to heat it back up, which means it'll be going in the exothermic direction. If I heat things up, it tries to cool it back down again. So that means absorb some of that heat energy. So it will go in the endothermic direction. So by seeing what happens both to the position of the syringe and the colour in here, we should be able to see or predict which one is endothermic, which reaction, the forward or reverse, and which one is exothermic. So first we'll go into iced water. So this is going to favour which reaction? Exothermic, because it's going to try and heat the system up again. Okay, so we'll try and, typical, it's going to be difficult to do with what we've got here. Shouldn't take long to have a change. Try and put this behind so you can see any change in colour. It's been quite as dramatic as the light, so just put a little bit more ice in there. I think I can see a colour change starting to happen now. what would you say about the intensity of the colour?
It's lightened.
It's getting lighter.
Mm.
Okay, even though it's, the particles are slowing down, as it were, it's getting lighter. Okay, so that would suggest, you're very much at the bottom. You can see it now, can't you? Okay, so that would suggest that the forward reaction is exothermic because it is favoured when I decrease the temperature. So conversely, what would I expect to happen when I put it into hot water? It'll get darker because it'll favour the reverse reaction. Let's see. Now, from memory, this is a little bit more dramatic to see as well. It pushes my syringe away as well because, of course, the reverse reaction has more gas particles in it. That, combined with the increased kinetic energy of the particles, is why our syringe is being pushed away, and it is considerably darker than it was, isn't it? Okay. So temperature and pressure can have an effect on an equilibrium, a dynamic equilibrium system, if it involves gases. Pressure, by the way, has no effect if it doesn't have gases in it. Okay. This is what we call the Chetalier's principle. Chetalier's principle, in a nutshell, states that if you change a dynamic equilibrium, the reaction, the forward or the reverse reaction, the reaction that undoes the change will be favoured. Alright, so if I was to pump more NO2 into here, it wouldn't go lots darker because by adding more it'll favour the forward reaction, so some of those molecules will automatically turn into N2O4. I've added more NO2, it'll make more N2O4 to undo that as best as it can. Alright. Likewise, if I was able to remove NO2, its colour won't drop dramatically because N2O4 molecules will become NO2 again to undo that change that I've made. Right, so that in a nutshell is the Chetalier's principle. Next period you're going to be looking at one yourselves, where you're going to be looking at the iron thiocyanate equilibrium.